Hello everyone, welcome back to Math with Allison. Today we're going to be working on our integration series, so we're going to be talking about definite integrals, so this is going to be a great introduction. So let's go ahead and dive into it. Here we want to talk about displacement using Riemann sum. I think this is a great way to introduce definite integrals. So let's go ahead and dive into it. So we have our x-axis represents the time in seconds, and the y-axis represents the velocity in meters per second. So when we use Riemann sums, we're estimating the area between the curve and the x-axis. So what I mean by that is that we can create rectangles, right, between all of these portions, and this is going to give an estimate of the area underneath the curve. But what is this actually finding? So let's go ahead and take this area, for example. When we find this area, we're going to go ahead and multiply the height times the length. I already know the length is going to be 1 because it's between 3 and 4 seconds. But what is our height going to be? This is going to be by plugging in the time into our velocity function. So here we have a time of 3, which we can see by this height right here. It goes up to our velocity function, and so we're going to go ahead and plug that in. So that's equal to 3 squared, which is equal to 9. So now I know the area is going to be the length times the height. So let's go ahead and plug that in. We have 1 second, and we're multiplying that by 9 meters per second. So notice here that the seconds cancel out, and we're just left with 9 meters. So when we integrate velocity, when we integrate the speed, we get position. But when we're using Riemann sums, we're missing quite a bit of area. We're missing all this area up here, or up here. Or sometimes we're overestimating. We're going way above. An example of overestimating would be if we did these types. So this is a right-sided Riemann sum. And now we're way overestimating. Look at all of this area that we're adding on. But that's not between the function and the x-axis. All we care about is this area right here. So what would happen if we made all these rectangles smaller? What would happen if we were to continue decreasing the length? I tried my best to draw in little rectangles, but when we decrease the length of them, so we make them skinnier, we're going to get a more accurate estimation of the area under the curve. So that leads us to what a definite integral is. Here we take the Riemann sum, right? This is going to be the summation of the area between all of those curves. So these right here represents the height. We're taking the function height, and this right here represents the length. And right here, this means we're adding them all up. So we're adding up all of the areas of the rectangles, but we're also taking the limit as n goes to infinity. We're making our rectangles smaller and smaller. When we add more rectangles, obviously they're going to get skinnier to fit all of those new rectangles. And this is what our definite integral is equal to. So let's go ahead and break down a definite integral. So the dx represents the length of our rectangles. It represents a super, super tiny sliver of it. So it's like if I were to take a tiny little sliver. That length is equal to delta x, and the height is equal to f of x. We go up to our function in order to get the height. Now, what does the integral of a to b mean? That means we're starting at a and we're ending at b. And so this gives us the area between the function and the x-axis. So let's go ahead and talk about other things we need for a definite integral. We need f of x to be continuous over a to b in order to integrate it. So here we have an example of a discontinuous function. We would not be able to integrate it like this. That is not allowed. Instead, we would have to break it up at c. So we'd have to go a to c f of x dx and then add on c to b f of x dx. We cannot do it together because we have a discontinuity. We also need that f has to be bounded on the interval. So here we have an example of a vertical asymptote. And the reason that we need it to be bounded is because this up here is going to have infinite area. It's never going to stop, and that we cannot have, right? And so this one we would not be able to integrate it. So it has to be bounded as well. So let's go ahead and go through an example here. We have a function which I drew out, and I also gave its areas. So here we have this first area is 12. The second one is 10, but think about it. It is underneath the x-axis. We'll come back to that. And then our other little one is 8. So first we're going to go ahead and find the integral between a to b of our function. So if we start at a and work our way to b, we're going to first get this first area. And I know that this is equal to 12. Now, if we go from b to c, we're going to start right here. We're going to work our way down and stop right here. Now, since this is beneath the x-axis, this is actually going to be negative 10. So we can get negative area in this case, and it has to do with the heights. we're not necessarily working with geometric area, we're working with algebraic area. And so this right here, if I were to draw a little rectangle inside of it, this right here is equal to the length, and it's going to be positive, right? Because we're moving left to right. But now our height is going to be negative because we're going into the negative y area. So we could pretend like this is equal to -2. It would have a height of -2. So this does result in negative areas. Okay, so now we're going to go ahead and combine these two areas. We're going to go all the way from A to C. Now what we do is we take the corresponding area, so we add them together, 12 plus -10. That is equal to 12 minus 10, which is equal to 2. Now we're going to go ahead and do the same thing, but instead we're going to start at B and we're going to go all the way to D. So when we add those areas, we start at -10 and we add 8, and this is equal to -2. So like I said, it's totally fine to have negative area because we're working with algebraic area, not geometric. Let's go through how we can actually solve for the antiderivative. So what we're used to right now is we're taking the integral of 2x plus 4 in terms of x. Let's go ahead and do that first because that's something we know how to do, right? So when I take the antiderivative, I get 2x squared divided by 2, or just x squared if you'd like, plus 4x plus some constant c. So this is equal to x squared plus 4x plus c. Now the difference is when we add bounds, here we're starting at 1 and we're going up to 3. Now we're going to go ahead and plug those bounds in. And so this is how we do this. We start with the upper bound and we plug it in everywhere we see an x. So I'm going to plug in 3. We get 3 squared plus 4 times 3 plus c. And then we subtract the lower bound plugged in. So when I plug in the lower bound, I get 1 squared plus 4 times 1 plus c. Let's go ahead and simplify that out. Okay, so notice here, actually the c's cancel out because we have a plus and a minus, and then 21 minus 5 is equal to 16. So I'm going to give you guys a little trick. When we're taking a definite integral, you don't even need to write the plus c anymore because every single time that c is just going to go ahead and get canceled out. So we're a bit more lazier with definite integrals. We don't write the plus c. So I'll go ahead and show you what that looks like officially. I took the antiderivative, I get x squared plus 4x, and I'm integrating this between 1 and 3. So here I plug in my upper bound, and I also plug in my lower bound, but I subtract that. So that's a bit cleaner way to do it. We don't need that plus c. And let's go ahead and take a look at the graphs. So here we have what we're originally taking the antiderivative of, and we are finding the area between x equals 1 and x is equal to 3. And so that area right here is going to be represented right here. And so this is equal to a value of 16. So we also have the antiderivative, which we can see represented with this blue function right here. So let's talk about why this is significant. So what we're doing is we're plugging in the value of 3. So here when I plug in x is equal to 3, I get this corresponding y value of 21. And that value is represented right here. Here's our 21. Now we're going to go ahead and subtract when we plug in that value 1. So let's see what that looks like on the graph. Here we can see it with our function, but when we plug in a value 1, we get a value of 5. So here we take the whole distance of 21 and we subtract that value 5, and this right here is what we're left with, which is a value of 16. And that also represents the area underneath the graph right here. Let's go through some more geometric examples. Here we have the integral from -1 to 2 of the negative absolute value of x. We don't always know how to integrate it, so it's totally fine to draw a picture and actually calculate the area. So what we have here is the area between -1 and 2 of our function. And we can go ahead and calculate this area using triangles. So I know the area of a triangle is equal to 1/2 base times height. The base of this triangle is equal to 1, but the height of it is equal to -1. Remember that we always work left to right. So when we work this way, our base is +1, but we're still going down, which gives us a -1 height. So here, this area is going to be equal to -1/2. Now let's go ahead and find the area for the second triangle. Again, we're working left to right, so this one's going to have a base of 2, but it's going to have a height of -2. So we get 1/2 2 times -2, which that cancels out and we get -2. So this one has an area of -2. When we want to find the entire integral, we just add on these two areas. So here we get -1/2 minus 2, which is equal to -2.5, or if you like fractions, -5/2. So we can also calculate the area using a graph. Let's go ahead and try another one. Here we have the square root of 16 minus x squared, and we're calculating the area between 0 and 4. So here I already drew the picture. If you're wondering how you can draw the picture, you can always just plug in x values. When I plug in a value of -4, I get 16 minus -4 squared. That's equal to 16 minus 16, which is a square root of 0, which is 0. Same thing when I plug in 4, you can just plug and chug. So we're going to go ahead and calculate the area of a semicircle. So the area of a circle is equal to pi r squared, but we're taking the area of half a circle. So actually it's going to be pi r squared divided by 2. So let's go ahead and plug in what the radius is equal to. If we're working left to right, we have a radius equal to 4. And here we also have that we're above the x-axis, so we don't need to worry about it being negative. So here we have the area is equal to pi times 4 squared divided by 2, which is equal to 16 pi divided by 2, or 8 pi. So this is what our definite integral is equal to. Let's go ahead and do one more. We have a piecewise function, which I already drew out, and we want to calculate the area of the function between 0 and 4. So let's go ahead and do that. If you wanted to, you can definitely do this by finding all these different areas. If you wanted, you could split this into 2 rectangles, 1 rectangle and a triangle, however you want to do it. Or we can do it like how we did the first problem. So here I'm first going to go ahead and separate this into 2 integrals because we have 2 different functions, right? So between 0 and 2, we're integrating 5 in terms of x. And now between 2 and 4, we're integrating 3x minus 1 all in terms of x. So let's go ahead and do this thing. First, when I take the antiderivative of 5, I tag on that value of x, and we're evaluating it between 0 and 2. Now let's go ahead and take the antiderivative of 3x minus 1. This becomes 3x squared divided by 2 minus x, and here we're calculating it between 2 and 4. So let's go ahead and plug in these values. When we have 5x, first I plug in that value of 2, and I subtract when we plug in 0. Now I'm going to go ahead and do the second one. First we have 3 times 4 squared divided by 2 minus 4, and I'm going to subtract on that lower value. So here I have 3 times 2 squared divided by 2 minus 2. Now we just get to go do algebra. So I get 10 minus 0 plus, and let's go ahead and calculate this right here. So here I got an area of 26. Let's go ahead and calculate that in the actual function. First, I'm just going to go ahead and calculate this whole area. The area of this guy is going to be the length times the height. So I have a length of 4 and a height of 5, right? Because that's our function evaluated at 5. So that first area is going to be 20. And now let's go ahead and calculate the area of the triangle. So I know this length is going to be equal to 2 because we start at 2 and we go to 4. Now let's go ahead and find what the height is equal to. When I plug in this point into the function, we get 3 times 4 minus 1, which is equal to 11. So that means this goes up to a value of 11. And the distance between 5 and 11 is equal to 6. So now let's go ahead and calculate that area. So we first have an area of 20, and that represents the rectangle, and then we have an area of 6. And so the total area, or the integral between 0 and 4 of f of x dx, is going to be equal to 20 plus 6, which is equal to 26. So you can do it either way. Both of them totally check out. That's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.